Good afternoon, everyone. Yeah, today I'll be telling you about the consequences of the Riemann hypothesis. Quick introduction to what the Riemann hypothesis is. So the Riemann hypothesis is a mathematical conjecture that was proposed by German mathematician Bernhard Riemann in 1859. And in its most simplest terms, it states the following. The zeros of the Riemann-zeta function can only occur at negative even integers, which are referred to as the trivial zeros, and certain complex numbers with real parts of 1/2, which we refer to as the non-trivial zeros. So there's quite a bit to unpack there, but hopefully by the end of the presentation, you'll kind of understand what all that means. So in my talk, I'll be discussing the following. So I'm going to give you a quick introduction to complex numbers, as I believe they're quite integral to understanding the Riemann hypothesis. Then I'll talk about the Riemann-zeta function, which is what the Riemann hypothesis revolves around. And then I'll talk about some properties that this function has, like its zeros and its poles. And then I'll talk about its connection to other fields of mathematics and physics. And then I'll kind of sum it all off, like telling you why you should care. Like, and to be honest, even if you just acknowledge the existence of the Riemann hypothesis, that's good enough for me. So starting off with complex numbers. So in the most basic terms, then complex numbers are these special kinds of numbers that can be described using these two components, the real component and the imaginary component. And they're typically expressed in the form a plus bi, where a and b are real numbers, and I is defined as the square root of -1, because it just is. So I've prepared this little graphic here that kind of should hopefully give you an intuition to what the complex plane is. So basically, you can think about this as like a coordinate plane with these two axes, the real axis, which you can think about as like your number line that you might be familiar with. And you've got this perpendicular axis, which is referred to as the imaginary axis, which is in terms of this unit I that I mentioned before. So the main takeaway from this diagram is that every point on this plane, it corresponds to a complex number. So let's take this point, for example. In order to get to this point, then we have to go 2 along the real axis and 1 up the imaginary axis. So we call this point 2 plus 1i, or just 2 plus i. Similarly with this point, -3 along the real axis and -2 along the imaginary axis. So we call this point -3 minus 2i. So I think that's probably enough you need to know about complex numbers in order to understand what I'm going to talk about. So moving on to the Riemann-zeta function. The Riemann-zeta function, which is denoted zeta of s, is defined using the following formula. Now, the actual specifics of the formula aren't really important, so all you really need to know is that it's a function that takes in a number and it outputs a number. That's kind of all you need to know for the sake of what I'm going to talk about. So coming back to the Riemann hypothesis, then what it concerns itself with is finding where the zeros of this function lie, which is basically saying what numbers you put into this function in order to get out 0. And so it's already been proven that every negative even integer is a 0 of this function, so like -2, -4, etc. However, there are also other values that have been discovered that also make the function equal to 0. And we call these the non-trivial zeros. And the one thing that's basically, all the non-trivial zeros that have been discovered so far, they lie on this line in the complex plane called the critical line. And so basically what the Riemann hypothesis is asking is, do they all lie on this critical line? So I've got a diagram on the next slide that will kind of illustrate what I'm talking about. So those are the trivial zeros, the zeros I mentioned before, which are negative even integers, like -2, -4, etc. Then here's this critical line I was talking about earlier on, which is just a vertical line in the complex plane, which corresponds to every complex number with a real part of 1/2. So basically all like the small dots on this line, they correspond to all the known non-trivial zeros of the Riemann-zeta function. So all the ones that have been discovered so far lie on this critical line. So in order to prove the Riemann hypothesis, then you basically have to prove that every non-trivial zero lies on this line. And if you were to if you even found the one zero that even lied slightly off the line, that would be completely disprove the hypothesis entirely. So if you were to solve the Riemann hypothesis, then it will tell you a lot about other fields of mathematics. And I think the most prominent one, most like well-known one, is probably how it connects to the distribution of prime numbers. And so let me introduce to you this function called the prime counting function, which is denoted pi of x, because I guess we just run out of letters at this point. And so basically what this function does is it takes in an integer and it outputs the number of primes that are lesser than or equal to it. So if I were to put in 3, for example, then my output would be 2, since there's 2 prime numbers that are less than or equal to 3, them being 2 and 3. And so, yeah, as you can see on the graph, this is the graph for the prime counting function, and it's got this kind of staircase look to it, because since it's only defined at whole value, like whole number values, then it's got this kind of staircase look to it. So in my research, I was able to find out that you can actually construct this function using the zeros of the Riemann-zeta function. So the way you do this is you use this equation called the Riemann harmonic converter, which looks really scary, but basically what this does is it takes in a number x and it outputs basically what is a mathematical wave. So we denote this t of x, and if we consider the following sum, so if we take the t value of 1 and we subtract the infinite sum of these t of s values, so these s values are the non-trivial zeros of the Riemann-zeta function. And so if we expand this out, so this just becomes t of 1 minus t of the first Riemann 0 minus t of the second Riemann 0, and so on. Then it will actually produce this prime counting function. So I was able to find a very kind of crude graphic that kind of illustrates this. So as you can see, as we increment our k value, then this wave kind of more closely approximates this staircase. And if you remember from before, this staircase like kind of graph is the graph for the prime counting function. So there are other ways that there's a connection that has a connection to prime numbers, but this was probably the most easiest to illustrate. And so if we look beyond mathematics and beyond number theory, then I was able to find 3 other fields where the Riemann hypothesis has at least some impact, them being cryptography, quantum physics, and classical physics. And if we start with cryptography first, which is just the kind of which concerns itself with encrypting data for like data transfer and stuff. So one of the most popular techniques for encrypting data is called RSA coding. And basically what this relies on is factoring very large numbers into 2 distinct prime numbers. And so the reason why it's used is because there's not really an efficient algorithm for performing this. So if you were to encode something using RSA encoding, then it would usually be quite secure. But it has been theorized that if we were to come up with a proof for the Riemann hypothesis, then there might be some step within that proof that would be able to tell us about making an efficient algorithm for essentially performing this operation of like splitting prime numbers or splitting these large numbers into their distinct primes, which would make RSA encoded data a lot less secure, which would obviously have like implications with data security. So another field that I was able to find out about was how it impacts sort of quantum physics, and specifically the certain state of matter, which is called the Bose-Einstein condensate. Now I could probably do an entire talk on what the Bose-Einstein condensate is. So just for the sake of this talk, it's a very exotic state of matter that can only exist in these certain conditions. So I was able to find out that you can actually make the following statement on the number of particles in a Bose-Einstein condensate. So it might look a bit scary, but basically what this can tell us is this can tell us a lot about how a Bose-Einstein condensate forms and the conditions necessary. So the main thing that this equation tells us is that Bose-Einstein condensate cannot form in dimensions lower than 3. And this is due to certain properties that this Riemann-zeta function has. And so if we were to solve the Riemann hypothesis, that would tell us a lot about how this function behaves, which will then give us a greater intuition to how this Bose-Einstein condensate can form. And so by having the best understanding of the Bose-Einstein condensate, then we can, perhaps apply it to real-world scenarios. And so I was able to find 3 scenarios where the Bose-Einstein condensate has been used. The first one being superfluids, which are, as it's been observed that Bose-Einstein condensates, they act as fluids with like 0 viscosity. So the one thing I was able to take away from that was you could potentially use them for like really high efficiency lubricants, which would lead to very high efficiency mechanical systems. And the second thing I was able to find out about was these objects called atomic lasers, which basically take essentially a blob of Bose-Einstein condensate and kind of shape it into this laser-like structure. And so, and these laser-like structures are really like precise, so we could be able to use these to essentially like take very precise measurements and produce high-resolution imaging of very fine structures. And the other thing that I was able to find out about is how it can be used in the development of quantum computing. So Bose-Einstein condensates can be used to study the conditions at which these quantum calculations can operate, and with how kind of profound quantum computing is becoming day by day, then this could potentially have quite a profound like effect on their development too. So I know I said I would talk about classical physics and how it can be used to how it applies here, but the one scenario I was able to find out about, which is modeling a billiard ball bouncing around a round table, it's mathematically way too complicated for the sake of this talk. Like I'd be here forever if I included it. So, however, if you do want to read about that, I've got a QR code at the end of this presentation that leads to a paper about that, so you can check that out. So, as I've previously discussed, the definitive answer to the Riemann hypothesis would tell us a lot about these fields that I've mentioned before, like cryptography and quantum physics and prime number distribution. And so it might not be immediately obvious at first, but if we were to innovate in these fields, then that would most likely lead to technological development within these fields. And so such developments could potentially impact our everyday lives with in perhaps the not too distant future. Also, if you were to solve this Riemann hypothesis, then you'd be awarded a $1 million prize by the Clay Maths Institute. So, that might give you some motivation to at least have a look at it. And so, before I end off, I've got these QR codes that you can scan. So, this one has a playlist I've compiled of videos that kind of go more in depth into the Riemann hypothesis, because it's kind of hard to go that in depth within 10 minutes. So if you do want to look more in depth, then there's a QR code for that. And then there's also a QR code for this book that I found out about, which basically talks more about the connections that the Riemann hypothesis has with prime numbers. And then this one leads to some papers that I saw when I was doing my research. So, and also one of these papers includes the example with the billiard ball. So if you want to look more into that, I would recommend reading these. And so, thank you very much for listening.